Hi everyone, welcome back to another tutorial. This is still for the 3.1 practical internal. This tutorial is probably going to be more useful to those students doing their second attempt. So I've done the first attempt, everyone's done it, and I can go over my report because I managed to get everything pretty right. And this video will also be focusing on the discussion specifically for those that are wanting to get excellence. So I'm just going to go over some things. I've written here some notes on basically the different grade levels, some real bad mistakes that people made that got them a terrible grade. So you can have a read through if you want. I'll just pause briefly on each one. You can see there's some good things that they did that got them that grade, and then towards the end there'll be some bad things that they could have worked on, right? So, sort of this stuff. For those people that almost got excellence, it was probably their discussion wasn't that good enough, so they probably got either E- or high merit. They just need to bring in some more relevant points. So we skip all this because everyone knows how to do it already. And this uncertainties of the independent and dependent variable. Please don't use the 4% thingy. Some people still got confused on that. Just use the lowest standard uncertainty. And in this case, it was the separation distance. So it would be 1 millimeter, which is 0.001 meters. And then the formula, same formula, power factor also. It is -1, but for all power factors, you just absolute value it, so ignore negative, so it's just 1, which is basically just nothing. And then obviously rounding it to 1SF. If you round it wrong, you will end up with an achieved. That's the graph. That's the mathematical equation. Now my y-intercept was actually really small, as you can see here. That was my y-intercept, but the rounding rules apply. My y-intercept uncertainty I calculated as 0.3. This has to match the same dp, right? So you can't just have something like this, okay? That doesn't work. This uncertainty always needs to be 1SF, and then that just needs to be match the same dp. Now, if you didn't round that correctly, you would have only ended up with an achieved. So it's really important you know how to do that. Same for this bit here. Same dp, and that also needs to be 1SF, right? And obviously don't write y next for your variables. Write the proper variables, which was the time period and the transform separation distance. And then that was the theoretical stuff. Now a really bad mistake which some people made is that they got confused between percentage uncertainties and absolute uncertainties. Now remember, a percentage uncertainty is basically just the absolute uncertainty multiplied by 100, right? So some people thought they found the absolute uncertainty when they had actually got the percentage uncertainty. So please don't get confused. That right there is my absolute uncertainty of the variable L. This section's calculating the variable L. And then to turn it into a percentage uncertainty, you just multiply it by 100. And then in the end, when you found your two percentage uncertainties, so that's for L, and then that's for the rod, you would take these two percentages, add them together, which gets you that. Oh. And then you would divide it by 100, right? Not multiply, and that would turn it back to an absolute uncertainty. And then you multiply that absolute uncertainty by your theoretical gradient, right? Theoretical G, and then that gives you your uncertainty rounded to 1SF. So just be careful, don't get the two confused. Okay, now the main purpose of this video was probably to go over the discussion, so we're going to walk through it. So, if I pull up the schedule really quickly, I've got an improved schedule. The excellence, to get excellence, you need to have two really strong points, so two secure points, or three E minuses. So which means you talked about 3 things to a average level, but still good enough, right? If you're aiming for excellence, I suggest you try and talk about all 4 categories. Don't just like sort of, talk about 2 and then give up, because if they're not very good, you're going to end up getting a merit. So the 4 sections I've already highlighted here is other variables. You also need to talk about how it affects the results and how it could have changed the results. And that is all backed up with physics, right? Everything has to be backed up with physics reasoning. Next section is the limitations, right? This is where you sort of talk about what the theoretical equation assumes and what's actually going to happen when you do the practical, and especially forces and stuff like that, damping, that sort of ties in. And this is a really good opportunity for you to link it to the practical situation. So in this context, in this assessment, it was trying to model a swinging log on 2 chains. So you would need to link it to that and how the practical compares to that actual real world situation. Then the third section is unexpected outcomes, which is usually you just talk about the y-intercept, because the theoretical equation does not include a y-intercept, so that is unexpected. Other difficulties, if I can spell. So you could talk about maybe using a different uncertainty. I'll just go over it now, okay? Alright, first one. Other uncontrolled variables. This is the first section. So this whole thing here is part of that one section, right? That first section here, the other variables. The first thing I talked about was the irregular sideways motion of the rod during the oscillations. So usually these other variables are things you notice when you're doing your practical that could affect the accuracy of your results and data. And you obviously need to back it up and explain it in a physical sense, right? So if the rod was released unevenly, part of the motion became translational and linear rather than purely rotational, which is what the theoretical equation wants it to be, right? Purely rotational. And then I talked about how it changed the oscillation path and made it difficult to determine when one oscillation has happened. So linking it back to how it could affect the accuracy, right? And then talking about when the effect was most notable. And then talking about how it could also affect the data and what would happen. So that was the first section of the uncontrolled variables. And then I also talked about the suspension strings possessing small amounts of unbalanced length. So the theory expects that the strings, if I get my pen, should look something like this, right? They should both be parallel, and then you've got your rod here, right? They expect those strings to be perfectly vertical, but sometimes you may have not noticed, but it might have been slightly not vertical, and that is what contributed to that extra translational motion. So linking it back to the other variable, and then talking about how it could shift the rod's center of rotation and inertia. Yet again, the theoretical equation assumes that the center of rotation is fixed, right? But if the movement becomes translational, it's actually going to shift that center of rotation. And inertia is just basically how easy something can rotate. So if it's got a higher inertia, it's going to spin slower, which is going to increase the time period. So therefore your data points are going to be slightly higher above the trend line. And if you've got a lower inertia, the opposite's going to happen. And then you'll also notice at the end, I've also suggested a way to improve upon this. So by using a level to confirm the strings are perfectly vertical. And then so forth. And in this one as well, movement of people, you can read that, but it's pretty much the same thing. How it affects the results. Right? That's all you need to talk about. You need to talk about what you observe, how it affects the accuracy and results, and maybe how you could improve upon it. Those are the only 3 things you really need to talk about. And try and, link it to physics in some way, especially, forces, center of rotation, inertia. Integrate some physics in there so you're not just rambling, okay? The next one is the limitations section, which was quite long. This is probably the most difficult section. The first thing I did was link it to the real world context, right? So talking about the scale of it, obviously a ruler with 2 strings compared to an entire log with 2 chains, it's massively different in size, right? So obviously that makes it less reliable. And also talking about energy, so here's me linking it to physics again. If energy is lost in any way, the energy would be lost at a much larger scale than the model. And then talking about people as well, walking on the log, that's going to change the size and location of the force they apply, which will therefore change the center of mass and center of rotation. You see how I'm consistently linking it back to what the theory equation assumes to show how the two are different and cannot apply. And then that's more physics there. And as you can see here, theoretical equation assumes the oscillating object has a constant center of mass, right? And then extreme values of the independent variable is still part of that limitation section. You can see it's right there. You don't have to talk about it because it says and or. So this second section here, right? There's basically 3 parts to it. You've got your limitations, and then you've got your link to real world, pretty much, which is like comparing it to the actual situation. And then you've got extreme values of the independent variable. Right? Those 3 things are included in that whole section. So that second section is actually quite difficult to get excellence for. If we go back. And then talking about what happened if I made the separation distance too short or too long, and how that would affect the reliability of the practical, right? And then here's the unexpected outcome. So that's its own entire section as well. If you go down here, this one's quite easy. It's usually just talking about the y-intercept. So I talked about how in my line of best fit, which is my graph, there's a tiny y-intercept, which does not align with the theoretical formula, because the theoretical formula has 0 y-intercept. And then you can't just say like, oh, this was caused by systematic errors, right? That's too vague for excellence. You actually need to explain why it's happening. So if you just write, oh, it's caused by errors or stopwatch errors, that's not enough, okay? Here's me linking to physics again. This is what the critical thinking's all about. So it didn't take into account all the unwanted forces that cause energy losses, right? Stuff like this. This introduced non-ideal motion, which was that linear motion we talked about before. And then how it would affect it. You can see this is how it would affect the data, this section here. And then I proposed a solution on how we could maybe fix it. So lubricating the rod to make friction have very little effect, which would reduce the amount of damping, which would give us a more accurate result. And then the last one, other difficulties. Now, usually I would have used the standard uncertainty of length as 0.001. But I chose to use 0.002 because of the knot as well, taking that into account. And also, it's really difficult to align it perfectly. So there's going to be a larger uncertainty. So I thought to make it a bit more accurate, I'd use a larger standard uncertainty. And talking about here how the calculated gradient may be higher or lower than the expected value, especially when you plug in when you're comparing the gradients here, right? This uncertainty is going to be a bit different depending on the standard uncertainty. That's basically it. Yeah, I hope you found this video useful.